we are okay. Now we're going to do the experimental values in the simulation. Unnecessary line on the table. Let's see here. Theoretical instrumental values, table 1. Turn on the switch, right? We're going to turn on the switch of the simulation. Here you go. Turn on the switch. Current flowing, arrows going through it. Conventional. Check the box for conventional, which is the direction of the current, and the battery symbol. Battery symbol. Oh yeah, we can do the battery symbol. I don't see it. And the batteries, turn the switch on, check the box for conventional values and the battery symbol. Why is that? Where is that? I don't see battery symbol here. Yeah, if you find out where the battery, oh, here you go. That's the battery symbol. Right in here. Okay, here you go. I don't know, I prefer this one. See the resistor symbol, That's the switch right in here. Okay, they're all the symbols. See that? Resistor, light bulb. Oh, that's how the light bulb symbol is. Wire, switch, and more. Okay? Pencil. Oh, you know what? I prefer this one. But if you're going to read at the diagram, at the circuit diagram, that's how they display in the circuit diagram. Remember, scientists and engineers, they are lazy people. So they invent those symbols, those simple symbols, to simplify the work, to cut down the amount of work to draw a circuit diagram. Okay? That's what they do. Let me take out, we're not going to show the current. Here you go. That's how the circuit looks like. That's how the circuit looks like. Very similar to what I had in there in my own PowerPoint. If I want to open the circuit, right? I open the switch, close the switch, close the switch. When I show the current superimposed over the circuit diagram. The current becomes superimposed over the circuit diagram. So let's work on that one. But I want to turn off the current so you can start get familiar with the circuit diagram. Okay, here you go. Okay, in the last virtual lab, you were introduced how you connect a ammeter and a voltmeter in a circuit to measure the current through and the potential difference across a resistor for each resistor R1 and R2. For each resistor R1 and R2, by connecting the ammeter and the voltmeter accordingly, measure the current, the potential difference, and the potential difference. What's the source current? Record the values, okay? And the second table. Here you go, second table right in here. So what we are going to do, let's start with the current, the ammeter. Let's start with the ammeter. Don't worry about the voltmeter yet. Okay? And what we're going to do, we are going to connect the ammeter at different spots of the circuit. Okay? So let's go here to my, what you're going to do, I am going to connect the ammeter just after the battery. That would be the source. Ooh. Be careful, be careful. Be careful, be careful. Here you go. Let's see if I can rotate it now. Here you go. Huh, how do I rotate it? Here you go. Right in there. That's the ammeter. And then I can connect other ammeters too. We can connect an ammeter after the resistor 1. I can do that. Let's cut this wire and connect an ammeter right in here. Okay? So here you go. Here you go. See, the current is the same. 0.03, was that what we calculated? Let's see. It's just that what we calculated. Numerical value, yeah, 0.034. I'm gonna have one more decimal in there, but the value is the same, right? The ammeter rounded down to 0.03. And I'm going to connect the third ammeter here. We do all that type of experiment in the lab, actual experiment, real life experiment. Connect, you go. What's going on here? Huh. Yeah, I hate that. Why this guy doesn't straight up? Let's see, maybe we gotta cut it loose first. Yeah, I want it to be in straight line. Here you go down, here you go. 3 ammeters. Okay? They are all the same. So go ahead and log in into that table. IS is the one next to the battery or to the source. I1, the one soon after the resistor 1. I2, the one soon after the second resistor. And then we're going to measure the electric potential. Remember, the current is like the gatekeeper, right? The ammeter is just like the gatekeeper. You gotta connect the ammeter in series with the circuit. Now the electric potential, remember they measure, actually it's the electric potential difference. That's the right name for the potential. Is the potential difference. That's the right name, but we usually say just potential to short it up. Because we are measuring electric potential difference, we gotta get measurements from 2 different points. And because it's 2 different points, we have to connect the voltmeter in parallel. Let's do that. Voltmeter, here you go. Always connect the positive, the red one is the positive, facing the positive of the battery. See? Positive is at a higher potential. That's why the plate is longer. Lower potential, the plate is shorter. Okay? And then we connect here to the other one. Hey, we're getting only 0. Why is that? Oh, I'm measuring the wrong spot. Sorry, folks. I'm getting from the multimeter, from the ammeter. You shouldn't do that. You gotta do across the resistor, not the multimeter, right? Okay, it can be either here or here. It can be here as well. The ammeter has no resistance whatsoever. That's an ideal ammeter. Okay? And the wires too, all those wires has no resistance whatsoever. Okay? Ideal wires has no resistance whatsoever. So much that when I measure the electric potential across the wire, we get a 0 drop in voltage. Wires, ideal wires have no resistance whatsoever. Ideal ammeters have no resistance whatsoever. Real ammeters, real wires have a negligible resistance. Okay? Here you go. So that's what we get for resistor number 2. Let's do for the resistor number 1. I'm going to do that again, okay? Across the switch. Okay? The switch has a closed switch has a 0 resistance. But if I open the switch, we get a minus 5 volts voltage. Why is that? It is like measuring the voltage between those two ends of the battery. Okay? But if you were to measure the resistance here would be different. The resistance would be infinity. Here you go. Let's close it. Now we got, but we want to measure the drop of voltage across this first resistor. And by the way, don't forget the red should face the positive of the battery. The black should face the negative of the battery. Let me close that. I'm gonna cut down the amount of wires. What's going on here? Yeah. Huh, interesting. Yeah, leave it this way. Okay. So remember we calculated higher resistor, higher drop in voltage. Lower resistor, low drop in voltage. 3.4 plus 1.6 is going to be 5. What is inputted here, what is gained here, is lost here plus here. So go ahead, complete your table, and you're going to get the same values that we got theoretically. Okay. Next. Turn the switch on. Let's see. Turn the switch on. Check the box. Okay. Yeah, I did that, right? I turned the switch on. After performing this step, for example, I see the screenshot. Turn the switch on. Check the box. Yeah, we did that. The last virtual lab, you were introduced how you connected. Yeah, we did that using the theoretical and experimental results in table 1. Find the theoretical and experimental power supplied by the power source and power loss in the resistors. Show your work in the space provided. Theoretical value. How we calculate the power. Okay, that's something we're going to cover in the lecture as well. There is a formula for the power. Actually, there are 3 different equations that we can apply. Here you go. The first one, I'm going to do that here in my lab notes. Okay. Power. Let's see if I already have it here. I have it here. Yeah, I have all the calculations here for you, right? Okay, here you go. The power is given by this equation. We can derive that. It's possible to derive. Now, using the Ohm's law, okay, V equal to Ri. Here you go. I'm going to put that. It's possible, like I said, it's possible to calculate this power. Now, using the equation Ohm's law, V equal to Ri, and substituting it right here in this equation, okay, we can get a different format of this formula. Rii, or Ri squared. Okay? That's a different format of the same equation. But we could also write this formula in a third different format. This equation here is exactly the same as this one. It's just a different format. But we could write this equation in a third format. Okay? How do we do that? We here write the Ohm's law, but now in terms of the current. Okay? V divided by R. And we here write the power. V over R. Move. And that's a third format of the same equation. VI Ri squared V over R. Okay. So go ahead, calculate the power of the source, which is the power of the battery. Power is, through resistor number 1, and power through resistor number 2. Okay? Let me see if I calculate that for you. No, I didn't calculate numerically, unfortunately. Yeah, I don't see it. But I'm going to do in the other one. Oh. Okay. Experimental value. He doesn't say how we do the experimental values here. That's an interesting situation here. I don't see any way of measuring the power lost here. Okay. There is no instrument here to measure. Oh, okay, I know how he does. Okay. The way he does, the experimental value. What's the experimental value? Okay. What you're going to do here for the power is the following. You're going to use VI, and you're going to use VI for the theoretical value. 5 volts times I of the source. That's what you're going to do. That's what he called the theoretical value. And then you use the same formula, VI, but using the experimental values here that you measured. Okay? That's what he means by experimental value, because there is no way. Experimental value, strictly speaking, experimental value should be something that you should measure with a power meter. But he didn't include a power meter here. Okay? He didn't include a power meter here. But you should, since you are getting the same values, numerical values for the experimental values and the theoretical value, you should get the same power value. Okay. Let's, just a matter of doing calculations, right? Let's go ahead. Don't forget, oh, by the way, don't forget to put the units, okay? Don't forget to put the units here. Units. He didn't put that for you, you should put it. Units, everything unit there. I'm gonna be looking for that, okay? I'm gonna be looking for the unit whenever I correct that. Correct the lab report. You do the same here. And I'm gonna put it even in red, boldface red. So you know it's something that's supposed to be there, but it's not. We go red, bold. Doesn't change much, does it? Red and bold. Here you go, put the unit there. What's the unit for power? Just like the regular power that we saw in mechanics. Okay, It's the same unit of power, but it just happens that it's electric power. The unit is no different. We use the unit of watts in mechanics. You also use the unit for watts in electricity, for power in electricity. Here you go. What's the total power lost in the resistors, and how does it relate to the power supplied by the source, the battery? We can prove that mathematically, that the power lost here in this resistor per the power lost in this resistor is going to be equal to the power provided by the battery. It's possible to prove that mathematically. Okay? So we must have conservation of energy. Let's show that mathematically how it goes. Okay, here you go. PS must be equal to P1 plus P2. So how do we prove that mathematically? Okay, the power in the source or the battery is going to be given by VI. The power in 1 and 2 is going to be given by R1 I square. The power lost in the second resistor is going to be given by R2 I square. Substituting those values right in here, we are supposed to get the same equation. Let's see if we get. We gotta prove that R1 is square, R1 I square, right? R2 I square. But remember, V1 is Ri. Remember that? V1 is Ri, so you end up with V1 times I. And similarly, we get V2 times I. We put I in evidence, and we get what? V1 plus V2, but V1 plus V2 is V. Which is exactly this solution right here. That's what you must have, conservation of energy. Next, did all the measured values and voltage agree with your theoretical calculation? Okay, it should, right? Use the same formula, same value, the values for the experimental values for the voltage and current. If not, identify which values did not agree and explain what you think. Okay, that's the first part of this simulation. I want to clean up my desktop here. Okay, I'm going to take out the ammeter. So we have a simpler, here you go, ammeter. Huh. Okay, now put it here. Too many wires. Let's see if I can extend it. Yeah, I can. Good. I want to extend this one as well. Yep. That's the circuit we have. I want to cut this one, too many wires. Ideally, in a real life circuit, we are always trying to minimize the amount of wires that you get in your circuit. Otherwise, you go crazy handling so many wires. That's what we do in real life, and that's what I'm doing here as well. Minimizing the wires in my simulation. All right, here you go. Wires, wires, here you go. Wires, here you go. Wires. Let's go to the next one. Part 2, resistors in parallel. Now we are going to put the resistors in parallel. The same resistor values, 147, but they are going to be in parallel. Let's go ahead and here's the simulation. Values, I'm going to put values here. Okay, check the values so you know what is what. Okay, and I'm going to cut this one. The name resistors in parallel is exactly what it means, exactly how it looks like in real life. I'm gonna cut this circuit. Let's put a wire here. There you go. Okay. Here you go. Doesn't look like it's in parallel. Here you go. Those are the circuits in parallel. Let me put a little wire here. I don't like the battery so close to the corner. Here you go.